I can start again from this slide. Basically, the idea of guided generation, or we call conditional generation or controllable generation, is that beyond the image, we also have an additional input y, and this y could be a class label or could be a text sequence in the text to image generation task, and we generated the image or the data X according to this Y, which means that we are trying to model the conditional probability P of X given Y instead of the marginal probability PX. And that's the conditional generation. And we hope the generated images follows the guidance of Y. Typical examples like let's say the first figure is that we generate the images from their class label, like we generate birds or deer. And the second example is that we generate the images according to the grayscale. And also in the portrait example, we generate the portrait according to whether they have color. So yeah, that's the idea of guided or conditional generation. So let's do a quick recap of the score-based diffusion model before we go deep to the guided generation, because it is easier to understand the principle of guided generation from the score-based model perspective. Okay, but before diffusion model, people when do the generation, people basically model the likelihood, which is the marginal probability of the data set or the image. And actually, we are trying to maximize this probability, maximize this likelihood to achieve to make up a model that can generate the similar images like the data set. And from the implementation wise, we basically have a model F, which is parametered by some neural network, and the parameters could be the theta, and we do a normalization here to make the probability between zero to 1. But as we know that as many our previous presentations goes, actually this Z theta is basically intractable in practice. So in previous works like the VAE, people are trying to approximate this likelihood with some bounds or some other approximations. And but by doing that, they can bypass the modeling of this normalization factor, so then they can make all the generation model differentiable and tractable. But in diffusion model, people find that okay, maybe we don't need to model the probability, the likelihood, the marginal probability. Instead, we can model the gradient of the log marginal probability, and this is called the score function. And if we have a model that can learn or represent the score function, we call it as a score-based model. That's why we call it score-based diffusion model. And this score-based model, we denote it as S, and it could be a neural network which is parametered by some, let's say, by some parameters theta. And this model is used to, model or represent or capture the gradient of the log marginal probability, and this gradient is over the data itself, the X. And if we expand this, if we bring the model, the neural network we use here, into this score function, we can find that we can try to reduce the model just like as doing a gradient over X for the original neural network we have, and that's the score model, score-based model we can have in diffusion model. And the goal is to we because we are trying to model the gradient of this this log likelihood. So the principle is that we hope our score-based model can predict this score can well predict this score, and so we can use some distance function to measure that. And from the optimized, but this one is hard to optimize. So in practice, people use a technique called score matching to optimize this score-based model to the desired desired output is that this S can well predict this gradient of log likelihood, and that's the score-based diffusion model. Based on that, let's build up the conditional generation principle. As we said, then the conditional generation is that we are okay, here should be P of X given Y. I'm sorry for that. P of X given Y, because we are trying to model the conditional probability. And yeah, P of X given Y. And if we use a simple Bayesian rule to expand this conditional probability, we will have something like this. This is just simple Bayes rule. And if we take a log for both sides, and we expand them, then we can have something like this, right? This just take a log. And again, we take a gradient over X for both sides. We can have gradient of X for this term, for the second term, for the first term in the right side, and for the second term in the right side. But for the third term, we can remove it because there's no X in this term. And if we take a gradient over X, then the gradient will be 0, right? So then we can have something like this. And in this case, we can see some interesting observation. Let's first look at the last one. This one is basically the score function we have here, right? If we train a standard score-based diffusion model, we already have this. And the left side, the conditional score is our goal. We are trying to, this is what we want, the conditional score, right? And it seems that if we have the original standard diffusion model, which we call as unconditional score here to differentiate it from the conditional score, we call it as unconditional score. Then if we have that, the only thing we need is one further term, which is we call it as guidance term. And this guidance term is P of Y given X, is that we have X, we want to know the label of this X, right? So that is an interesting observation, means that seems that we can first get the unconditional score, which is easy, just a standard score-based diffusion model. And secondly, we need a way to model this guidance term. If we can do that, then we can just plus them together to get our goal, right? But how should we do that? So far, any question?
Is very similar to the gradient expansion. Why does X will be classified into?
Yes. Okay. That's a good observation, and that's why we call it as classifier guidance. Is that okay? Now we are trying to introduce the classifier guidance paper, which is from OpenAI on NeurIPS 21. Okay. Again, now we are trying to model this guidance term. So, but what is that? Just like Ido just said, basically it is a standard classifier, right? It's discriminative model. Is that a given image? Note that in the diffusion model, because we are doing the denoising step, so the noise in some intermediate stage, the image could be noisy, but that doesn't matter. Is that for this classifier, for this guidance term, we have a image X, and we want to predict the corresponding Y, so which is a label. So what's this? This is just a standard classifier, right? It could be neural network, could be CNN, could be ResNet, could be anything. Just like as a standard model we use to classify some images, right? So if this is the case, then things become very easy. We can train a diffusion model as the unconditional score, and then we train a classifier to represent this guidance term, and then we just plus them together. Then we can have the conditional score, right? And actually, that's the idea of classifier guidance. And because this P of y given x is basically the classifier, and that's why we call this model as classifier guidance.
We got the conditional score. We just add that in the context.
Yeah. Yes. Yes.
Now after that,
yes. Yes. Okay. So basically, actually, that is about the procedure of this one. Is that we train unconditional model, the diffusion model, and at the same time we train the classifier. This is during the training. And when we do the sampling stage in the denoising diffusion model, we just sum up them together in the sampling stage. Then we can have the conditional score, the conditional generation. This is our goal, and this is also called post hoc conditional, because the post means that post training, right? We only combine them in the sampling stage. And this is the idea of the classifier-based classifier guidance. So how should we add this guidance term into the unconditional score? Okay, now let's change the notation a little bit. Is that previously we don't consider the time step in the diffusion model, but we know that diffusion model is step by step. So we generate the for example, in the sampling stage, we are trying to denoising step by step, right? So we generate a new image from the noisy image in the previous step. So let's bring the time step back. Is that because the sampling is the inverse, is in the inverse direction. So then we have we generate xt given by based on xt plus 1, and also we have the label. Then we just expand them, and recall that in diffusion model we model this one-step generation as a Gaussian distribution, right? So suppose this is what we have for one-step generation, and if we take a log, the Gaussian distribution can be rewritten as something like this. Yeah, that's what we know before, right? Okay, now let's look at this one. This is our goal, the conditional generation in one step, and we know that it has two terms. The first one is same with what we have before, just the generation from previous noisy image, and the second is the classifier, right? And now let's do it. Also, we take a log for this classifier probability, and now we do a Taylor expansion for this one. And we only keep the first two terms in the expansion. Then we can have something like this. And the Taylor expansion is around the mu. The mu is the mean value of the Gaussian distribution here. Then we can have something like this. And this G is just this term. To simplify it, we denote it as G. And then the conditional score, see here, this is our goal, right? Because we are trying to generate this conditional score. So we take a log here and we can take a log here. Then we can have something like this. We can just, because this one is a log, and we can just split as log p theta x given xt, xt given xt plus 1, and plus log p theta of y given xt, right? So we can just, for the first term we have here, For the second term, this is what we have here. Then we just sum up them together. Then after some metric duration, we can finally have something like this. And this is log P of Z. Z is the another Gaussian distribution whose mean is a little bit shift from the mu, and the offset of the shift is modeled by the G, and G is the classifier. Okay, this is what I didn't figure out. I don't know how to do the calculation here. Yeah, but for the next step, and this one is simple. But anyway, we can see the idea is that we can model the conditional score by a new Gaussian distribution, and the new Gaussian distribution compared to the unconditional generation, we only shift the average of the Gaussian distribution by modeled by this classifier. Okay. And actually, this is what Shichang covers before, is that in the paper, actually, this is the sampling stage. But based on what we have here, we can rewrite the sampling stage of a standard diffusion model into a conditional diffusion model. Is that when we do the sampling, we only add a new term, the shift, as the guidance at the mean value of the Gaussian distribution. And this guidance, this offset of this shift is given by the classifier. Okay. So that's the condition of the classifier conditional generation. So let's do a quick conclusion. Is that during the training, we train an unconditional diffusion model, and at the same time, we also train a classifier to predict the label Y in each time step. So because this note that there is a T subscript for X, so XT is the image, is a noisy image at each time step. So during the training, we have two models, diffusion model and classifier. And during the sampling, we just do the denoising. We just do the denoising by this following this algorithm, which means that we sample from the diffusion model, and then we plus some offset given by the classifier, and then we can do the sampling, do the final sampling, and that's the classifier based, conditional generation. And actually, for the model architecture of the classifier is pretty flexible. Basically, you can, because we are just trying to model the conditional, we're just trying to predict the image label, right? So whatever model architecture you can use is flexible. And in this paper, they use a similar architecture with the diffusion part is the UNet with some attention.
Hi, Song. Can I ask a deep question?
Yes.
So I understand this kind of this classifier, right? Actually modifies the mean, right? Why they this part, right? So that's from the classifier, right?
Yes.
Why does it not change the variance?
Why it does not change the variance? Oh, okay. This is because here from the duration, we basically what we have is finally we have finally get something like this. So if we fully understand this derivation, then we know we only actually shift the mean instead of the variance. But I don't know how we could.
I'm trying to understand why the variance keeps the same.
Okay, maybe we can I can show some intuitive example here. Okay, let's say this one is that the left figure is unconditional. Is that we generate from without any guidance. So suppose we have three three kind of images, and their distribution looks like this. And if we have the guidance, we basically shift them. We make them far from each other, but we may not change the variance of each class. And this is some intuitive understanding. Okay, but for the rigorous part, it's because we get from this duration, so that we know we only change the average, but instead of the the variance.
Okay.
Okay.
But just reading this formula essentially is log of the probability of 2. So the second part actually is not a Gaussian noise, not a Gaussian distribution. So there's no covariance matrix there.
You mean this one is the second part?
The second part is what given as the classifier.
Oh, okay.
Does this sigma that covariance matrix related to the Gaussian distribution?
Oh, I see.
Yijo,
I mean this one actually.
I can barely hear Yijo. Song, can you repeat what Yijo said?
You think about a Y, right? Most likely it's like discrete, like class labels. But for your X T, cannot confuse. So you can follow Gaussian distribution. And the first line of that, the log of the multiplication of the two probabilities for the second one. Actually, if you go from the second line to the first line, the proof is much easier. This is the groups that xt minus mu as one term, and the sigma g as second term. Just extend it.
Oh, I see. I see.
I think from first to second does like g minus 1 feels like identity, and the multiply sigma minus 1 sigma, that is also identity. Insert it inside, I think you can get it. That's a commentary.
Okay.
Then multiply by sigma minus 1. So that's is identity.
Oh.
Sigma inverse and
Would you want to try that?
Hi, Song, could you please summarize what Yijo and the other student said?
Oh yeah, we are basically.
I couldn't hear.
Okay. Yeah, basically, Yijo suggest what Yijo said is that if we look at this formula,
Yeah.
the second term is basically a classifier. It's not related to the sigma, the variance.
Right. So
the
it's
variance is only from the Gaussian distribution, which is here. Yeah.
I see.
Oh, yes. I'm sorry. I would say the sigma is only from here, and the second term is this classifier, and there's no sigma in this term.
It's not.
And yeah,
so that's what.
Yeah. Then from student, Zhicheng just mentioned one trick to do the derivation from this line to the second line, and he's writing on that. Maybe he can share with us later.
Okay.
Yeah.
Thank you.
Yeah. Okay. Yeah. Any questions so far? Okay. And then let's see how this classifier guidance works. This is some figure from CIFAR, I forgot from which data set, or from ImageNet, and the right column, this column is the ground truth image, And the left column is one baseline, which is the one of the SOTA generation model with the GAN architecture called big GAN. And this second, the middle column is the classifier guidance diffusion model. And we can see this one roughly focus more on the object itself. Right. So here I have a question for all of you. And this is not from paper, it's just what I was thinking when reading this figure. This is okay, the left part is the big GAN, right? And this middle is the guidance, the classifier guidance. So if we can observe that the classifier guidance model, they are zoomed in, they are more zoomed in to some local area of the object, right? Compared to the big GAN, right? So why it is this case? There's no exact answer. I just have some personal thoughts. Any thoughts? Any ideas? Okay. Okay. Again, this is just my thought, and it could be wrong. Okay. Let's look at the guidance term. Is that let's try to understand this. Without this guidance term, we basically generate or do the sampling from the standard Gaussian distribution for one step, right? But with this guidance term, this is gradient term. So what they provide us is that they move our image, or we are changing the image because this is a gradient of the image. We are trying to change the image towards the direction that can maximize this guidance term. And this guidance term is, again, is a classifier. So it means that we are trying to move towards the image area or the image direction that can maximize this classifier, this probability. So the question is, which local area or which part can maximize this P of y given x? And we see a lot of such examples. Is that from image, if we choose CNN or whatever CV classifier model, they basically only focus on the object, right? Then can, instead of the environment, then can differentiate or is really the why this image belongs to some label. For example, here the fox is the model only looks at this part. Means that from the classifier perspective, this part, this fox part, is the part that can maximize this conditional probability. So go back to this example, is this head that can make the classifier know, okay, this what label does this image belong to? And that's why, you know, this gradient will towards those areas. And that's why, you know, because we are directly change the image based on this gradient of data. And that's why the generated data moves towards those local areas. Does that make sense? That's my thoughts, and it could be wrong. No, this is just my observation and what I'm thinking when reading this paper.
So we just take the second rule as one example. I see that I'm not sure whether this is all the pieces are running or not, but if you see the original training examples, it seems like there are more zoomed in pictures.
Yes, but what I'm saying is that compared to the GAN style baselines, why the diffusion model, the guidance diffusion model is more zoomed in on the local area. So because it focuses, because we have this classifier, so it makes us to focus more on the part that can, you know, determine the image label, and that's why I'm thinking we should. That's why I'm thinking why the classifier guidance focus more on such areas. Yeah.
So,
anyway,
so which data set? So for this figure, which data set it is used to generate?
If I recall correctly, it should be ImageNet.
So they're also utilizing the classifier trained on ImageNet.
They use the classifier trained on they use the classifier trained on the same data set because this training is along with the diffusion model training. It's not a pre-trained model.
And the right column is the training set.
The right, yes.
Yeah, then it is not that we might not saying that the second column might not might be too zoom in because it is more similar to the third column, right?
Okay, depends on your understanding. But again, we don't need to stop here too much because this is just my thoughts. If you don't disagree, if you don't agree, because just my thoughts, you know. Yeah, but if this is the case, then this may cause some failure when the classifier rely on some shortcut learning or spurious correlation. And this is an example that we may know that sometimes the classifier model may not focus on the object, but focus on the environment as a shortcut or spurious correlation to predict the label. And in that case, if that is the case, then this generation may not focus on the object, for example, the call, but may be generated a little bit on the green environment. Okay. Yeah, also this is also my thought, maybe wrong. And second, this is also another thought from me, is that what's the relation of this classifier guidance diffusion model to GAN? Because we know that this classifier is basically the discriminator in GAN, right? Especially when we do the sampling, we are fixing the parameters of this classifier. We just use this classifier to judge or to give the probability. So this is basically the same step as what we use the discriminator in GAN. Because we fix the discriminator, we use it to provide some guidance to the generator, but this is definitely in different schema. But what I'm saying is that here the guidance, the classifier guidance, is basically a discriminator. So yeah, that may also explain why it works well. Yes, the Y is different. The Y is different. Mm-hmm. It's not it's trained with the diffusion model. It's not a pre-trained model, because in pre-trained model you don't have a noisy image, right? Because this classifier should give you the label Y for every noisy data in every time step. Because we have for every noisy image, we have the Y, because Y is always the same for one image.
I thought we're going to pre-train this Y, which is the classifier. And then for any XT, you can always output that dependent probability in any Y. So the label, you're going to have, of course, like conditional generation, you have to specify Y. But it's not about a sign label.
Okay, for every data, we first we have the Y, the label, and when we do the adding noise procedure, in the diffusion model, for example, we have many time steps. We can have many images from this original image with different noisy levels, and all of those XT, their label Y is the same because they are from the same original image, and we train the classifier for every time step. that's why this is denoted by py given xt.
If you look at the algorithm one,
Mm-hmm.
it says given a diffusion model, result train,
Mm-hmm.
and given a classifier, result.
Oh.
Given a scale, how you can generate the image.
Because this algorithm one is the sampling stage, it's not about the training.
Then, from just a reading algorithm one, you can touch the part how you can train the diffusion model and the classify, and could be pre-trained. From algorithm one, cannot tell how they can train to just slide that.
Actually, yeah, because it's very obvious. So I just put the training part. I didn't show the algorithm of the training part because training a diffusion model, we already know that, and training a classifier is
Right.
standard.
They could be trained separately. And this like image and the label, they can just from ImageNet. You don't have to kind of combine the diffusion process as the classify training process. You don't have to.
Then in this case, the pre-trained classifier must be a noisy robust classifier. Otherwise, you cannot give me a noisy image. How should you predict the label Y?
So always predict the label Y given any.
Yeah, so maybe I can try this because I just read the paper. But I guess you two are talking about slightly different things. So I think what Song is saying is that our classifier later on will take some xt as an input, right? And xt is not the original image from ImageNet. It could be a very noisy image that we added with, right? So in order to have a good classifier on this kind of noisy image, during training, we need to train our classifier on this kind of noisy image.
Okay, so the slide does not touch that.
Okay.
Okay.
So then I think your point is like saying we can just generate a bunch of noisy image and train the classifier and have it separate from the diffusion process, right?
Yeah, it's just don't know like in practice, how do they?
At least in the paper, in their experiment section, they are saying that they train it on noisy images. So it's like you take image from ImageNet, but you add a noise on it.
You train new model.
You just add noise on it.
Yeah.
Then you can think of it as augmentation. You get a much more augmented data set, and then you train the classifier on that.
Okay, so for that, then you would have different practical actions. Like one possibility is to add regular noise. It does not have to connect to the diffusion model. You just add this also noise. And then you can just make the classifiers much more robust, but still could be independent of whatever. I think,
Yeah.
In order to really understand how they train the model, I think instead of just talking about the sampling part, we also need to use in practice how do they do the training.
Yeah, actually, yes, actually in this paper, they trained the classifier basically use basically not pre-trained model, but a model with the similar structure with the diffusion model. But this is just used as a classifier. If I recall correctly, they are training the data from along with the denoising, the adding noising part. Yeah.
How do they add like the regular white noise or more advanced noise?
Should be same with the diffusion model. Derek.
Oh yeah. So during the diffusion process, is it always the same classifier? Because I would think at the beginning it's more noisy.
Yeah. That's a good question because from the paper, they just said they train the model at every time step. So this is a little bit confused for me because I don't know they train one model that can handle every time step, or they train a classifier at every time step. Yeah, so this could be true. This part I'm not pretty sure for how they do this paper, but the idea is that they need to handle every time step of the noisy data. Yeah.
I think different time steps are different because in their text in the experiment section, the classifier actually takes in another parameter t, like xt and t. So like if T is large, you probably are stating that this image's noise level is really high.
No, T,
But in the algorithm, we somehow ignore that T, just have Y conditional X T.
T is another input, but does not mean they have different, does not essentially mean that they have different models. It could be just
Right.
one, time indicator.
Yeah, but that's like an additional argument telling you the
Yeah,
image, sorry, the noise level.
Right,
Yeah.
right. Yeah, so, but the point is that the classifier should handle the noisy data at every time step. Any other questions? Okay. And also, people are trying to control this conditional generation by adding some scaling factor. And for example, from the original generation principle, we can add a gamma here, which controls the strength of this classifier. And in practical, people find that if this gamma is pretty large, then the generation would be the quality would be pretty high, but also they lose some diversity. And if we do a quick reformat of this one, we put this gamma to the power of this log conditional probability, and we remove the log and the gradient. Basically, we can have something like that. So this one actually explain why we enlarge this gamma can help us get better quality examples. The better qualities in terms of that is more comfort to the label, to the Y. The reason is that if gamma is large enough, because this is a probability, right? It's from 0, so the value is from 0 to 1. And if the gamma is large enough, then the guidance, this conditional probability would become very sharper. Means that the larger value, the difference between larger value to small value will be amplified. For example, if the gamma just equals to 1, we may have, for example, the label 1, the probability of P of Y1 given X is 0.2, and P of Y2 given X is 0.1. And if this 0.2, 0.1 just 2 times, right? And if this gamma becomes 2, then they become 0.04 and 0.01, so 4 times. Means that the difference or a larger value, a larger conditional probability will be, the effect will be enlarged. That's why adding this gamma, adding a large gamma will help the quality the generation for high quality images. And but again, this is actually a trade-off, because when you increase the quantity with precision, they basically decrease the diversity or recall. And some the experiments in this paper also show this phenomenon. And for this one, we also explained how the scaling factor, the gamma, affect the distribution. Is that if with a larger lambda gamma, those those different groups, obviously those different class images, they become separated more from each other, so that when you do the sampling just from the, for example, if we invest in one denoising, we move some point around this area, then basically we will stay in this area. That's why we can generate more we can generate a higher quality but less diversity images. So far, any question? Okay, and this is all about image, but we know it's interesting that the classifier basically just give us some guidance that is a P of Y given X, right? So it does not, it means that, for example, in other applications like the test, this classifier could be some could include more information. For example, in this paper, which is this year's newest paper, they trying to use the parse tree as the classifier to provide the guidance into some language model diffusion language model. So this is for text. And for this year's iClear, there's a summation about the molecule generation. Is that they trying to design some with graph neural network or whatever, design a classifier that can predict the property of a molecule as the guidance. And if you put this classifier in this generation, you can imagine that the desired outcome is that it can generate some molecule that has some desired property, right? And when they design this classifier, you can use whatever what we already know in graph neural network, like the equivalent neural network, into this, to serve as the guidance. And this is the one recent paper from the graph generation using diffusion model. But we also see some limitations of the classifier guidance, and the typical and one limitation is that they cannot using the SOTA pre-trained classifier, and that this may also relate to our previous discussion. But the second one is most important, is that they require an extra classifier model, means that we need to train two models, right? So the complexity or the cost could be high. So a natural question is that, do we really need this classifier to provide the guidance? And the answer is yes. This is what we call the classifier-free guidance. The free means we don't need the classifier. And this paper is from Google Brain, and it came out July this year.
Hi, it's stop again.
How about now?
Still waiting.
There's my screen in the lab.
They just have like a little circle going around, saying you have started the screen sharing, but the screen doesn't show up.
How about now?
Yes.
So where did I stop? Okay. Anyway, here our motivation for classifier-free guidance is that we don't want to use extra classifier, but we still want to have the guidance. The idea is still from the this factor, right? This is the what we have in the classifier-based guidance with the scaling factor. And let's do a quick with Bayes rule, is that we expand the conditional probability of P of y given x with this, and then we do a similar. We take log for both sides, and we take the gradient for both sides. And now we say the previous guidance term is here, and the conditional and unconditional scores, they are here, right? And we just put this guidance term into the previous guidance term we have before, and then we can have something like this, right? Or we do some, we clean it as something, we can have an equation like this. So this is interesting, right? We know the left part is what we want. We want a conditional generation with some scaling factor, And the right part is that we look at the right part. We only have two terms. The first one is still the unconditional model, is the score-based diffusion model. And the second part is something the conditional generation is as what we want. But this is a general. For the left part of this, it has the scaling factor, right? So, but in this part, in the right part, the scaling factor is not in the model. It's just a coefficient here. So it seems that if we can have a model, if we can have a model, then it can both generate unconditional and conditional score. Then we don't need an extra classifier. Right. That's the idea of a classifier guidance model. And how they do that? How they do that is pretty simple. It's a pretty simple trick. And the author mentioned in the paper just change one line in their code, is that during the training, in some percentage of some time, the condition. Oh, okay. First, suppose we have a model, and this model have two inputs, is the X and Y. Okay, but during the training, in some time, we replace the conditional information Y with some specific input value, just as what we have in natural language, the SEP, the separate, or the CLS, right? We just replace, in some time, we replace the Y as some specific symbol to denote the missing of this condition, this guidance Y. And we just joint train this model. So interesting is that we still just have one model and there's no extra cost, but we can have a model that can handle the unconditional and conditional input simultaneously. And yeah, you know, for the standard model is that this model has two inputs, the X image and the label Y. And if we don't do in the normal case, we just have these two inputs and the Y is the label, right? But and sometimes we replace this Y as some specific, for example, just like the CLS notation, the token in the natural language.
So do concatenation?
We can, okay, I don't know, they do concatenation to one vector or they separate as just two input, but the point is one is X and one is Y.
So questions like, because X and Y are different. Y are labeled. So we different can do the diffusion model for X. Now, how to handle this discrete label Y is very important. Maybe with the same idea, like some people use next one and some other use two. Maybe one of them can be successful and others fail completely.
Okay.
Not because of the general idea is not right.
I see. I see. Okay. The paper, they, you know, when they provide this method, they are trying to do the text to image generation. So the Y is some embedding of the text caption. Yeah. So that's why they can. I guess this can somehow answer your question. But if the Y is a discrete label, yeah. Honestly, I don't know whether they're, you know, I mean the detailed technique they use.
Even for the label, I think it's a mention technology that we can turn it into a prompt, which can the label to still could be same.
Oh, so you mean then we can transform the discrete into some continuous representation?
That's one thing called the clean guidance.
Okay.
So that's like say you have an image label says bird, but they have a sentence saying that the following image is a.
Oh, I see.
And then you add a word to the.
I see.
Empty slot, and then you turn the whole sentence into that.
I see. I see.
So the clean model can embed that whole sentence into an embedding, which you can concatenate with the original image.
That makes sense. Okay. Yeah. Anyway, the point is that they, you know, trying to replace the Y and some probability. to make this model can both handle the unconditional and the conditional score. Okay, during the here, because this paper they use a different notation system, but the point is that here during the training, just the only thing we need to focus is that they just make with some probability they replace the y with some specific notation, like here the null set notation, and then all the others are the same with the standard differential training. If you say this, the procedure is a little bit different as what we know before, because because the implementation of different diffusion models, they have some difference in the details. Like here, they first sample the signal noise ratio and do the combine of the original image and the noisy. That's what some details about the anti-noising, but that's not the focus of here. And during the sampling, say the only difference is that they are trying to sample from they are doing the sampling twice. The first one is with the y. Here the ZT should be the x, the C should be the y. Okay, so ZT should be the xt, because they use different system of the notation.
Why we have the subtraction here? Earlier we said it should be weighted summation.
Weighted summation? Oh, you mean this one? Oh, because this okay. If we see here, if we put this 1 minus okay. Yeah, I put here is 1 minus gamma as minus omega minus w. We can rewrite this one as something like this. If you put 1 minus gamma as minus equals to minus w, then this one becomes minus w, and this gamma becomes w plus 1. Yeah, from two papers, and they use different notations. So here we just follow this one to do the sampling, and the point is that we need to do two rounds sampling. The first one is with the y, the C is y, the guidance, and the second part is without, which means we replace the y with some specific notation, because we need both scores to do the sampling. Right. Okay. Here is an interesting thing is that, remember this gamma, as we know before, is larger than 1. It is larger than 1. It works well. If it's larger than 1, then this 1 minus gamma is negative, right? And if we put a negative here, then this w is positive, right? Definitely this one is also positive. So this is positive minus positive. Again, this is still my thought. What does this one really means? For me, it looks like that we are trying to know the difference, because they are the w plus 1 and the w, they are both positive, right? So means that we want to know the difference between the conditional generation and the marginal probability, right? So if we imagine that everything can be added easily, they are compositional, basically means that we want to remove the marginal part, the general marginal part from the y, from the p of y given p of x given y, the conditional part, to keep the specific information related to y. That's my understanding. Yeah, and but that's the classifier-free guidance. So point is that we don't need an extra classifier. We only have one model, but the cost is that during the training, we need to do 2 rounds sampling, right? And in practice, people say this classifier-free guidance also works well. and the similar with the previous one, the scaling factor gamma also controls the the quantity of the guidance as what we have in the classifier guidance diffusion model. And the pros of classifier free model is that it's simple and we don't need to train an extra model. But the disadvantage is that we need to do the 2-round sampling. One is for one is with the Y, one is without the Y. And usually, but for classifier guidance, we only need one sampling, and we need to do one forward process of the classifier, which is usually much faster than a sampling. And that's why the sampling speed of classifier free model usually is not that good. Okay, questions?
For the last
Uh-huh.
There are 2 terms, right? One is after time.
Yeah.
So did they show any examples without the second term?
Without the sample, oh, okay.
I mean, without subtracting the second, because in the first one you already have both the X and the Y you want the condition of, right? Seems like the second term is doing some sort of calibration.
Mm-hmm.
So and also the second term doesn't depend on the condition.
Mm.
So I'm just thinking about if you already have a condition there and you don't do this kind of calibration.
Okay, the point is that how do you train such a conditional score, right? Maybe yes, you can just put all the Y during the standard diffusion model part, but
so this is for the sampling stage, right?
Mm-hmm.
So I guess at this point, my classifier 3 model is already.
I got what you mean. Okay, that's a good question.
Yeah, that's a good question.
Hmm.
So I think if we have enough downforce in plus Y, maybe the performance will be similar. But if for something like a video plus Y, then we really need to leverage the entire data set to build the model.
Would you guys think that this is because of the W, the scaling factor? Because
I prefer the first one. It makes more sense. Just the blend of the kind of global distribution with that conditional distribution.
Mhm.
So somehow you need to still rely on that.
Mhm. Oh, I see. You need to consider this condition of this label, but also the global.
Yeah,
This.
real class.
That's why you think the summation makes more sense.
Yeah, so of course, like the formulas are joint to use the next one too.
Mm-hmm. Okay.
So because in the previous classifier guidance, we have 2 terms, although one of them was like a Y data X, and then just to me those 2 terms, when you have classifier guidance, 2 terms are doing like rather more independent things. In this case, the second one already gives you some kind of path. That question is whether like how necessary it is to use this.
Mm.
I don't know, maybe this kind of question, unless we write something experiment, hard to know.
Mm-hmm. Okay. Any other questions?
Well, so I only have 6% bandwidth. Do you think, how can we make it as color? Because right now I just fear it's like correlation.
Let's do this. Let's do this. As okay. I want to show you just question about how to connect it with causal. So basically, one direction is that we can remove the the correlation, right, during the generation. And here is the daily true API I applied before. But before that, we let's see some good example. Let's see. Oh, no, this one. Oh, this one. What I write is compare San Francisco with Shanghai, drawing a book. Amazing, right? So if we only look at the figure, draw on a book, compare San Francisco with Shanghai. I cannot draw something like this. It's amazing for me. But again, just like what we know before, the semantic, the text is not that good. Right? This is a good example, but let's say what this is a good example. I really want to show to all of you then, because this figure buys me of the diffusion model. Okay, but let's say this one. Teddy bears shopping for grocery in Japan, UKU style. But this is a painting style, basically this style. So good, right? And let's say this one. A grocery store shop selling grocery store selling art, still the same style, also good, right? Let's see this one. A Japanese house built on cliff, still UKU style.